In today's lecture, we'll be looking at vectors and matrices. This is in no means a comprehensive discussion of vectors and matrices. This is just an introduction that will help us as we go through the NMR course. So let us first start with what are vectors. Any physical parameter that is associated with a magnitude and a direction is called a vector. And the one that is only associated with a magnitude is called a scalar. The basic example one can give in this category is speed versus velocity, where speed only has a magnitude, a vector in addition to the magnitude also has a direction. In a three-dimensional Cartesian space, I'm drawing a right-handed system x, y, and z. Let's say you have a vector that is v, for instance. We try to give it coordinates a, b, c, where a corresponds to x-axis, b corresponds to y-axis, and c corresponds to the z-axis. Alternatively, people also represent the vector as ai plus bj plus ck. Be aware of the fact that in addition to a, b, c, we also introduce a bunch of variables. Those are the entities that are given with a cap above it. So these are called unit vectors. Unit vectors are nothing but vectors that have a unit magnitude and the direction based on the coordinate or based on the axis that they belong to. For instance, the I cap represents the unit vector along x, j cap represents along y, and k cap represents along z. We are able to understand here that the a is the magnitude along the projection of the vector v along x-axis, and b is the projection of the vector v along the y-axis, and c is the projection of vector v along the z-axis. When we are talking about projections, immediately the thing that comes to our mind is the dot product. The dot product is also called a scalar product. The scalar product between two vectors, let's take a vector and b vector, is going to be denoted by mod of a, which is magnitude of a, mod of b, magnitude of b, times cos theta, where theta is the angle between two vectors. So let's take an example. There are two vectors a and b. That have an angle theta between them, then the dot product will actually be a scalar that comes out. That is why it's also called a scalar product. A dot a, this will be nothing but mod a square times cos of 0, that will be 1. Right? So therefore, mod of a can be determined by the square root of the dot product between a and a. So v is also represented as a, b, and c, meaning that you have the I, j, k as the unit vectors. The dot product between these two will end up being whatever you started with. Let's also take a quick look at how do dot products look as matrices. Remember, whatever we wrote here is in fact a matrix form. So now let's give some attributes. So let's say a vector is a1, a2, a3 for instance, and b vector is b1, b2, b3. So this can equally be represented as a1i plus a2j plus a3k. I'm skipping the denotation of caps here just for the sake of brevity, and here b1i plus b2j plus b3k. So when we take a dot product, that is a dot b, similar to the one that we had just seen a little earlier, I dot I will be 1, while I dot j, I dot k will be 0. So therefore, you are going to get something like a1 b1 plus a2 b2 plus a3 b3. So this is the dot product between the two vectors a and b. On the other hand, we can also do the same thing in the form of matrices. This will be a1, a2, a3 taken with a product with b transpose, which is column vector b1, b2, b3. This will once again result back in whatever you ended up getting here. So all that we are trying to show here is that the vectors can be represented in different forms, and there is correspondence across whatever you end up calculating for in the case of the dot product. So let's take a look at what is A cross B. This is called a cross product, also called a vector product, because you end up getting a vector. Similar to what we had for the dot product, you have the magnitudes of A times B times sine theta instead of cos theta, and you have an n cap, where this vector n cap is perpendicular to the plane containing A and B. So this is very important. So one can imagine when you're trying to open a cap of a bottle, you give forces that are perpendicular to each other, which ends up opening the bottle or in fact closing it. Remember, the motion of the cap is perpendicular to the forces that you end up applying. So that is basically what is cross product or vector product. So this can be expressed as a determinant I cap, j cap, k cap, a1, a2, a3, b1, b2, b3. So for the I cap, it is going to be these entities that end up interacting with one another, which is going to be I times a2 b3 minus b2 a3. And then you have a minus j, you interact these terms. So it's going to be a1 b3 minus b1 a3. And then once it comes to the k cap, it is going to be these two entities a1 b2 minus b1 a2. So what one is able to understand here, the cross product ends up giving a vector back, right? Unlike the dot product, which ended up giving a scalar. And we have been able to see when vectors are represented as matrices, how do the dot product and cross product come up? Let's even ask, what do these mean? A dot product is nothing but, let's say we have two vectors A and B that subtend an angle theta. A dot B is nothing but the projection of the vector, one vector on the other vector. Okay, so for instance, what is the projection of this on this vector or this on that vector? Okay, on the other hand, as I said, the cross product is going to result in another vector where when you apply two forces, let's say A and B, the resultant is going to be perpendicular to both A and B. Now let me show you an example with the help of a mathematical tool called Wolfram Alpha, which can be accessed from wolframalpha.com, where we will be trying to understand how these various products of dot product and cross product could be calculated. For instance, you are looking at two vectors here. This is one vector, well, this is another vector. This is vector 2i plus 3j plus 4k. On the other hand, this is a vector which is 3i plus 2j plus 1k. When you take the dot product, what ends up happening is what we will be trying to understand. Type the vectors with curly braces with a comma. 2 comma indicates that it's a three-dimensional vector. Same here, you have to only have vectors that have similar dimensions where you can take a dot product. The dot indicates that you can take a dot product between these two vectors, and you hit enter, and then what you are able to realize is that the dot product between these two vectors have been calculated and you get the net result of 16. It's very obvious because you have to multiply 2 with 3, 6, 2 with 3, 6, and 4 with 1. So you're going to get 6 plus 4, which is going to be 16. So similarly, why don't we take a look when we try to do the cross product between these two vectors? Unlike the dot that you ended up putting last time, here you have to type the word cross and you get the cross product between these two vectors and you get something like minus 5i, 10j and minus 5k. You are able to see that there is a blue vector here and the purple vector here. These two are your initial vectors, and the resultant vector comes up as the red vector, which is perpendicular to the plane containing these two vectors. Other concept that is going to be useful for us is matrix multiplication. We just saw one example where when you are taking the dot product between two vectors, you took the matrix multiplication as A dot A transpose. When you have a column vector, let's say you have n by 1 vector, the transpose just becomes a 1 by n vector, A11, A12, A13 and so on. Taking transpose of this matrix results in the diagonal elements remain the same, that is A11, A22 and A33. On the other hand, these two elements interchange positions. So this is going to be A12, This is going to be A21. Similarly, this is going to be A31 instead of A13. This is going to be A13, A23, A32. So what one is able to visualize here is that these are the entities that exchanged positions. So that's what is called a transpose. So now, why don't we take a look at how matrix multiplication across two matrices end up coming up, A11. I'm just going to be showing you one step in this entire multiplication rather than going into the entire detail, because that will take a little longer time. So the first element, so remember, you're multiplying a 3 by 3 matrix with a 3 by 3 matrix. Only if these two indices match, you will be able to multiply, and the resultant will be a matrix which is a final 3 by 3 matrix. Of course, you can always have a p by n times n by m. As long as these two indices match, you will end up getting a p by m matrix. So now, when you're trying to calculate this, the first element here is going to be determined by multiplying these components. The first element is going to be obtained by multiplying these components, A11, B11 plus A12, B21 plus A13, B31. So that is the first element. The next element of this is going to be once again taking this but multiplying with this one. So that's going to be A11, B12 plus A12, B22 plus A13, B32. The next one is going to be multiplying the row of the A vector with the third column of the B vector, which will give you the third element, and so on and so forth. So this will help you get an entire matrix. Once again, this can also be done in Wolfram alpha. Why don't we take a look at how that can be done? Let's write the first A matrix. That's A11, A12, A13. Remember, since it has more than one row, therefore you need to have another set of curly braces with a comma before it. A21, A22, A23. Finish the curly braces. On the third row, A31, A32, A33. The dot indicates the product that we want to take, and these two are the A and the B matrices that we have, and we are trying to get a product out of them. Wolfram alpha takes a few seconds to calculate this, and once again you are able to realize the representation of the A matrix and the B matrix here, and once again you are able to see three columns that are present, and you find three rows as well. So this is a 3 by 3 matrix. So there are some identities or features of matrices that are useful as we go forward. One is that a matrix, if it's a square matrix, its inverse can be calculated such that A times A inverse will give you identity. Remember, identity matrix depends upon dimensions. For instance, 1 by 1 identity matrix is just a 1, and a 2 by 2 identity matrix is going to be 1, 0, 0, 1, and a 3 by 3 identity matrix is going to be a 3 by 3 matrix with diagonal elements as 1 and all off diagonal elements as 0, and so on and so forth. You could have a higher dimensionality, and this A inverse is calculated, which I am not going to go in detail. You can use Wolfram alpha to calculate this as well. The A inverse is calculated by 1 by determinant A times adjoint of A. This is feasible for matrices that are square in nature. For non-square matrices, there are other ways of determining what is their inverse, which we will not be dealing with. Why don't we take a quick look at how inverse can be calculated using alpha. So let's pick some elements. So let's say 1, 2, 4, 3, 4, 3, 1, 2, 3, 1, 5. So let's take a look at this matrix. The way the determinant is calculated is take the first element and engage the ones that are present. So 15 minus 1 minus 2 4 times 5, which is 20, minus 3 times 1, which is 3, plus 4 times 1, that is 4, 3 times 3. So therefore you're going to have 14 minus 2 times 17, which is 34, plus 4 times minus 5, which is minus 20. So this is going to end up being minus 40. And you are able to realize the determinant value has been carefully calculated. After having found this, Wolfram alpha is also able to determine what is the inverse that ends up coming. Another important aspect to learn about matrices is that each of the matrices is characterized by their eigenvalues as well. Without going into much detail, eigenvalues are nothing but the fact that if the same matrix is written as a diagonal matrix, what would be the values for lambda 1, lambda 2, lambda 3? If you follow right procedures, you'll also be able to determine the eigenvalues, and you're able to see what are the eigenvalues for the matrix that has been given here. And remember, the important aspects of the matrices should be maintained. That is trace of the A matrix that you started with, which is nothing but the sum of diagonal elements. For a diagonal matrix, it's going to be lambda 1 plus lambda 2 plus lambda 3 must be equal to what you started with. The trace of the starting matrix is 1 plus 3 plus 5, which is what you get as 9. And let's try to take the sum of these three values. You will realize that that also comes up to 9. So before and after diagonalization, the value of the determinant, that is determinant A, should also remain same, which you ended up getting as 40. Now if you take the product of 8.15, sorry, minus 40, end up taking the product of 8.15 times 2.67 times minus 1.83, you will end up getting the value 40. So the two properties that should remain same before and after diagonalization is that the trace should remain same and the value of determinant should remain the same. The other aspects that the Wolfram alpha helps you get is how was the diagonal matrix obtained from the initial matrix. If the initial matrix is M, eigenvectors are calculated, and from the eigenvector calculation you will be able to determine what is the diagonal matrix. So let us wrap up this lecture by looking at a few more small aspects of matrices. When you have A is equal to A transpose, this is called a symmetric matrix. When A is equal to minus of A transpose, this is called a skew symmetric matrix. When a matrix A is equal to its own transpose and complex conjugate, where the star indicates a complex conjugate, then this matrix is called a Hermitian matrix. Let's quickly discuss what does this complex conjugate mean. When you have a complex number C plus ID, its complex conjugate is C minus ID, where the imaginary part, the sign inverts, while the real part remains the same where you started from. So let's take an example. When you have the A matrix as A11, A12, A13 and so on, its transpose would be its transpose would be 1, where the values of 2, 1 and 1, 2 would have interchanged, and 3, 1 and 1, 3 would have interchanged, and 2, 3 and 3, 2 would have interchanged. Remember, the diagonal remains the same. Now, if you take a complex conjugate, you're going to end up getting the complex conjugates of each one of these entities. So, when a matrix is Hermitian, you are able to realize that the diagonal elements AII, its complex conjugate, has to be equal to itself. So this immediately indicates that all diagonal elements are real. On the other hand, the off diagonal elements Aij transpose should be equal to Aj. So in this quick, short, brief lecture, you have been introduced to various aspects of vectors and matrices which should be useful towards the lectures in NMR spectroscopy.